All right, here are the solutions. Make sure that you've actually tried the problems on your own first and tried to correct them on your own first, and then take a look at the solutions. All right, here are the answers to the first couple of questions. These should be pretty straightforward. The only thing that I want to point out here is this second piece. It doesn't matter how large of a circle we use because the number of radians depends on the radius. So even if you make a really big circle and you travel, quite a distance around the arc of the circle, you make a really big, really long arc, you're still computing the number of radians by seeing how many radius lengths are in that arc length, and so it will end up creating the same angle you would have if you traveled the same number of radius lengths around a unit circle, which is why we use a unit circle. These should all be pretty straightforward as well. A couple things to point out. At 5 pi over 4, cosine and sine have the same value. Tangent of 17 pi over 2 is undefined. That's because 17 pi over 2 is in the same place as pi over 2, and so their tangent is undefined. And at negative pi, tangent has a value of 0, and it's nice to interpret it in terms of the slope of the terminal side. That'll allow you to see why the slope is 0. Here we have the Pythagorean identity, and that is that the cosine squared of theta plus the sine squared of theta is equal to 1 for any value of theta. And the reason that this is, to prove this, what we're going to realize is that for any angle, cosine and sine are the x and y coordinate, where the terminal side of the angle intersects the unit circle. So what we can do is we can draw the following right triangle. So here's some angle theta, some random angle, and sine is the y-coordinate, and cosine is the x-coordinate of this point here. So we can create a right triangle where the side lengths are cosine of that angle theta, sine of that angle theta, and then the hypotenuse is 1. So we simply apply the Pythagorean theorem to this right triangle, and you get cosine squared theta plus sine squared theta equals 1, which is the Pythagorean identity. Again here, nothing overly complicated. F of x I think is a little bit easier to work with here. Remember, we're visualizing first, so we have a sine curve. We are noticing that there's going to be amplitude of 3, midline of -1, and you notice here that the value of b is 1/2, multiplying x by 1/2, and so that means that the period is going to extend, it's going to stretch out a little bit. And so if you're envisioning this, sine starts at the midline and then increases and then hits its maximum and decreases. Anyways, we then go find the amplitude in the midline, 3 and y equals -1. That allows us to determine the max, which will be 2, and the minimum, which will be -4. The period is 2 pi divided by 1/2. 2 divided by 1/2 is 4, so you have 4 pi. And there is no phase shift. So then we can plot the first point, which is nice because there's no phase shift. Sine is going to have a y-intercept on its midline. There we have it. And then the next easiest thing to do is notice that since the period is 4 pi, the third midline intersection is going to occur 4 pi units to the right. And then halfway in between that, it's going to intersect the midline again, so that's at 2 pi. And then halfway in between these first two, there's going to be a maximum because sine starts increasing, and then there's going to be a minimum, and from there on out, we can sketch the curve pretty easily. For g of x, I'm going to just visualize first. We have a cosine function that is reflected. So cosine, remember, usually has a y-intercept at its maximum and starts to decrease. Because we're reflecting, we're going to have a y-intercept at the minimum and start to increase. So that's important. We'll notice there's a phase shift. We're going to have some sort of period that's different from 2 pi. Midline is 2, and the amplitude is 2. So midline of 2, amplitude of 2, that means our maximum is at 4, our minimum is at 0. The period is 2 pi divided by pi over 8, which is 16. And then we're going to have a phase shift of 2 units to the right. So I can plot my initial point, and the way I can do that is cosine usually has an initial value, a y-intercept, at the maximum. But it's been reflected, so it's going to be at the minimum. And it's phase shifted 2 units to the right, so that point at the minimum is going to move 2 units to the right, and that allows me to plot my first point. The period is 16, so it's going to have a minimum of 16 units to the right of 2, which is 18. And another 16 units to the right. 18 plus 16 is 34. I may have marked out a little bit too far to the right, but The intention was for this to be 34. And then you notice that cosine is usually a function which starts to decrease. But we have a reflection here, so it's going to begin by increasing. Another way to see that is in between two minimums, we're going to have a maximum. So a maximum is going to occur here, another maximum is going to occur here, and then I can just go ahead and plot my curve. All right, here we are applying the Pythagorean identity. We're told that the value of x is between 3 pi over 2 and 2 pi, which is in the fourth quadrant. In the fourth quadrant, cosine is of course positive, and sine is going to be negative. Finding sine of x, we can use the Pythagorean identity. Sine squared of x is 1 minus cosine squared. Cosine squared is 1 squared, 1, over 6 squared, which is 36. 1 minus 1/36 is 35 over 36. And then I need to square root both sides. So the operation that gets me from this equation to this equation is square rooting both sides. Now, when I square root both sides, I'm going to have square root of 35, as I have here, and then the square root of 36, which is 6. And I got to be careful. The Pythagorean identity does not determine the sign. I have to use the quadrant that I'm in to determine that. And since we're in the fourth quadrant, sign is negative. So this is going to be negative square root of 35 over 6, which is approximately negative 0.986. Finding the tangent, I'm going to take the sine, divide by the cosine, which is multiplying by the reciprocal of cosine. And that works nicely. I can use the exact value here because 6 over 6 is 1. So I have negative square root of 35, which is negative 5.916. And that should make sense because if I think about it, since the sine is very close to negative 1 and the cosine is actually very small, this is going to be a very steep slope here. And so I expect a pretty steep negative slope. That'll help me approximate the value of x, the angle. Since sine is very close to negative 1 and cosine is very close to 0, I would approximate x to be slightly greater than 3 pi over 2, since we're in the fourth quadrant and sine of x is very close to negative 1. All right, I want to create a sine and cosine function that corresponds to this graph below. Let's just take a look at the graph quickly. We'll notice a couple of things. The first is that the midline is at negative 1 and the amplitude is 2. So we can see here that the y-intercept is actually at the midline and then begins to increase. So this could be very easily made into a sine function. So we're going to go with a sine function first because there's no phase shift needed. So we'll start with a sine function. The midline we said was negative 1, so k is negative 1. The amplitude is 2, and so a we're going to say is 2. It doesn't look like we need a negative 2 since there's no reflection here. So we'll have 2 sine, and then negative 1 is the k value. What about the period? Well, let's look at the distance between two maximums. We can see here that this point is pi over 4 past 0, and this point here is pi over 4 past pi. So this distance is pi. Another way to see it is that the distance between the midline intersection here and the one that's 3 to the right is pi, or 2 to the right, I guess, is pi. And so that's another way to see the period, which is pi. Now, because the period is equal to pi, and we know that the period is 2 pi over b, we can solve for b. So pi is equal to 2 pi over b. 2 pi divided by what is pi? Well, 2. So b is 2, so I can now write my function y equals 2 sine of 2x, b value is 2, minus 1. Now, to turn this into a cosine function, I can do so easily because the sine of a value x is equal to cosine of x minus pi over 2. So I'm going to take my sine function, and I'm simply going to subtract pi over 2 from the argument. So I have sine of 2x, so it's going to be 2 cosine of 2x minus pi over 2 minus 1. Now you'll notice this looks a little different. Usually we have the b value factored out. We can do that. We could factor out a 2, and if you factor out a 2, you'll get x minus pi over 4. To see that this works, imagine we actually built the cosine function first. Notice that the maximum occurs pi over 4 units to the right of the y-axis. So we have a phase shift of pi over 4 units to the right, and that's exactly what this shows right here. All right, so creating a Ferris wheel, I'm not going to create one for you. I want this to be something that you kind of do on your own here. But the thing that is most important is that you pick a period. In other words, how long you want it to take for your cart to go all the way around. And so I would pick something that makes sense. Think about being on a Ferris wheel, maybe, 2 minutes or 5 minutes or whatever it is. And so that t is in seconds. So then you'll have to convert that to seconds. So if you want to take, 5 minutes to go around, 5 times 60, 300 seconds. And then you can compute the value of b much the way that we just did in the previous problem. And of course, draw your diagram of your Ferris wheel, determine how high above the ground you want it to be, how high up in the air you want it to go, and that will tell you, your midline and your amplitude, so on and so forth. All right, so here's the donut problem. We have a donut, the interior is circular and the exterior is circular. The radius of the interior circle is 1 inch, and the radius of the exterior circle is 4.2 inches. So of course the big hint here is that the interior circle is just a unit circle, and hopefully that will sort of clue you in to how you might attack this problem. But even if not, it should be pretty apparent if you simply follow the sort of instructions, if you will, of what Jason and Russell each do, and if you diagram the donut correctly, you should be able to tell pretty easily how you can compare how much of the donut each eats. So for Jason, I'm going to go ahead and diagram Jason here in green, and I will diagram Russell in light blue. So what Jason does is he measures around the inside of the donut here, and he measures 2.5 inches around the inside of the donut. So if the radius is 1 inch, I'm going to try and draw this to scale here. Let's say there's the center, and if this distance is 1 inch, then 2.5 inches might get him, I don't know, somewhere out here. Okay, so we'll say he travels like that, and that is 2.5 inches. All right, and then what he does is he extends a line from the center of the donut through his starting and ending points all the way to the exterior of the donut. So take that step by step. He extends lines from the center through his starting point to the exterior and through his ending point, which is right here, to the exterior. Just like that. Okay, then Russell, he does something very similar. He measures 10 inches from the point Q around the exterior, and if we know that the radius of the exterior circle is 4.2, so we know that this is 4.2, and I'll go ahead and label this. So the radius of the interior is 1, and the radius of the exterior, I'll mark that over here, is 4.2. That's a little light, but you see what I'm saying. So if this is 4.2 inches, then this might be another 4.2 inches, another 4.2 inches, I don't know, somewhere around here, it might be 10 inches. The point is I don't want to end up right in the exact same place because I want to be able to visualize the comparison between how much each eats. All right, and I'm just diagramming here. The diagram isn't going to tell me for sure which one eats more, but it's going to allow me to see how I can compare the two. So let's just say it ends up, I don't know, somewhere over here. So he travels around the exterior of the circle, he ends up there. So this distance that I'm outlining in light blue is 10 inches. Okay? And then he does the same thing. He extends a line from the center to his starting point and to his ending point on the exterior of the circle. Okay, now I went over that in purple because the light blue was a little hard to see. All right, and then each is going to eat the amount of donut that is between their starting point and ending point and along the arc. So let's just consider what that means for Jason. So this is the line at which he ends, and this is the line at which he begins, and the amount of donut that is along his arc is this donut here. For Russell, same idea. Along his arc, which is right there, is this amount of donut there. So based on our diagram, it's pretty easy to tell that if this was the mathematically exact amount that each ate, that Russell would end up eating more of the donut. Now, how do we actually compare that? What causes Russell, according to our diagram, to eat more than Jason? Well, it's pretty obvious because he has created an angle that is a little bit bigger, right? Whereas, as we can see, Jason's angle a little bit smaller. This should remind you of how we actually measure an angle. An angle is measured by the number of radius lengths in the arc that it creates. So for example, the angle that Jason creates, the arc length is 2.5 and the radius of his circle is 1. So the angle that he creates is an angle of 2.5 radians. Now Russell, he creates an angle of, well, we need to do a little math here to figure this out. And here's why. His arc length for his angle is 10 inches, but this is around a circle of radius 4.2. So to compute the angle that he creates, we need to see how many radius lengths of 4.2 are in 10. In other words, how many radians is the angle that he created. So we'll say that Russell creates an angle of 10 divided by 4.2, because that will tell us how many times 4.2, the radius, goes into the arc length of 10. And once we compare the two angles that each creates, we can see that Jason is taking up more of the donut than Russell would be, and so he's going to eat more of the donut. This actually isn't the only way to do this problem. You could also think about how you're taking a circle of radius 1 and extending it out to become a circle of radius 4.2. And so what you could do is multiply the dimensions here by 4.2. So you would multiply the arc length by 4.2, and 2.5 times 4.2 is greater than 10. It's in fact 10.5, and so that would be the arc length that Jason creates if he were to extend it all the way out to the exterior of the circle. And so that's another way to compare the two of them. But what's cool about this problem is it allows us to see how radian angle measures do not depend on how big of a circle you use to create them, because it's all about how many radius lengths are in the arc length that you create.